Introduction to graphs of sine and cosine, exercise 6D. Just to be clear, again, this is only on sine and cosine where the transformations are only dilations. So we haven't applied our reflections. Actually, no, we might apply reflections, but we won't apply our translations yet. Note that for the general form, and I'll ask you guys to write this down if you don't have it in your resource books already, well, where we have y equals to a cosine of nt, or we have y equals to a sine of nt, of course t being the value of our, like for example, let's say theta, there we go, period equals to 2 pi on n. We have our amplitude, and we're just going to write amp equals to negative a. Oops. You know what, I'm going to rewrite that. I'm going to write a, and then of course our range is going from negative a to a, and our maximal domain is just all real numbers. A lot of information to take down, but a lot of it's really intuitive. Of course, it being a sine and cosine, or cosine wave, sorry, it's going to go on forever unless you restrict the domain. So the maximal domain is, of course, all real numbers. The range, of course, in this format, it's only going to apply for where our amplitude exists, changing from the center of our graph. So for example, if it's going up 5, going down 5, well, the range would just be from negative 5 to positive 5. The most important one here to focus on is period, which is 2 pi on n. Of course, a quick reminder, period is the actual, period is a poor word to use in this definition, the actual value of t, or the range, the domain, we'll go with that, the domain values of t, for which our graph does not repeat. Okay, so for a graph, for example, goes on for a long time without repeating, perhaps it's a really long wavelength, for those of you that do physics out there, then it will have a very large period, whereas a very short period or very small period refers to a very, very short wavelength. Okay, so for this situation, we've got y equals to 2 sine 3x. Of course, the way I think about it is, what does x have to be in order for our graph to be the same without the dilation? So let's ignore the 2 for now, just focus on the 3. For my graph to be the same as y equals to 2 sine of x, my value of x must be 1/3 of what it was before. Does that make sense? In order for my graph to be the same as y equals 2 sine x, my value of x must be 1/3 of what it was before. I realize now there's a -2 here. I'm going to ignore that for now, just because we're introducing that stuff later in a later exercise. So y equals to sine 3x. So let's focus on finding our period first. So period equals to 2 pi on n. Of course, the value of n is just the number in front, or the coefficient of our variable. In this case, it's 3, so 2 pi on 3. If it was just 2 sine x, what would the value of n be? If it was just 2 sine x. Guys at the back. If it was just that, without the 3, of course, the value of n would be 1. So our period, normally speaking, is 2 pi. Normally speaking is 2 pi. However, we've restricted, we've changed it, it's now 2 pi on 3. So I'm going to very roughly sketch this out. In this exercise, there might be a certain domain. This is what you guys already know. Substitute to find endpoints, but I'm going to very roughly do it here. So of course, my amplitude is going to be 2, thank you. Which means that if I don't have a translation, which I've very conveniently crossed out. If we don't have a translation, we're going to assume, or let's start off and say, all right, sine graphs, do they start at 0 as a y value, or do they start at 1? 0, great. Thank you for that. Sine, of course, starts at 0, whereas cosine starts at the top. So let's start at 0. We know that a multiplication of an amplitude, so it could be amplitude of 100, it still starts there unless we've got some sort of translation. We know it goes up and then back down. Agreed? Great. What is... Let me fix that up. No, that's not what I meant to do. What is this value right there for t? 2 pi on 3. Because that is my period. Of course, that means in halfway through, it's going to be pi on 3. Remember, it is, generally speaking, symmetrical. Because our graphs follow something called a unit circle, which of course you guys know are symmetrical as well. What's this value up here going to be? What's the very top? 2. And the bottom one's going to be negative 2 as well. Great, you're done. If you have a very specific domain, so for example 0 to 2 pi, just do what you normally do, as in keep drawing this graph until you get to 2 pi. And if you don't know exactly where 2 pi is and it doesn't fit nicely in, substitute 2 pi into your equation and see what you get. That's how you find your endpoint, graph it, bam, done. Any questions about that? No? If I have a cosine, the only difference is instead of starting in the middle and going up and then back down, the only difference is with the cosine, you're going to end up at the top and come down and come back up to the top, where this is the middle of our period and this one will be the end of our period. And of course, if we've got a negative value in front, of course, what does that mean to our graph? Technically, yes, but more this way, correct. If it's a negative value, so for example, if you end up with negative 2 sine, I'm going to use this in different color. So if I end up with negative y equals to negative 2 sine 3x, we're reflecting across the x-axis or along the y-axis, and you end up with something that looks like that. Any questions? Sweet, super easy.